Welcome everyone. On behalf of East Central University, my name is Dr. Christine Pappas and I'm the chair of the Department of Politics, Law, and Society. I'm also the director of the Master's of Science degree in Water Resource Policy and Management. And it is my great pleasure to introduce Dr. Barney Austin, who will be delivering a public lecture on climate change, which is sponsored by the Oka Institute, also based at East Central University. So this lecture is part of our cumulative experience for our climate change and water class for the master's program. And it's also open to members of our community. So with no further ado, I'd like to introduce Dr. Barney Austin.
Thanks, Christine. It's a pleasure to be here as always. And when I say here, I guess it's a little different this year than last year. Normally, I like to be up on a stage interacting with my audience for these presentations. Having said that, it is kind of nice sitting down at my desk and being in shorts and flip-flops while delivering this presentation. But hopefully, there'll be a little bit of interaction with the audience at the end of the presentation. I've put together a few slides for this evening, and I've stolen a couple of slides from previous presentations. I wasn't sure how many members of the public would participate, but here's a very brief overview of the presentation. I plan to talk a little bit about terminology again and background, and then talk about observations of climate change, things that we are noticing already from observation networks. And analysis of data series. I'm going to talk a little bit about climate models and the energy imbalance caused by the greenhouse effect, and talk a little bit about feedback loops and tipping points, which are terms you've probably heard of before if you've looked into climate change at all, which you have with your class. Also want to talk about positive and negative impacts on climate change. There are both, of course. So I've got some examples I want to talk through. And then finally touch on mitigation and adaptation. So I've got quite a few slides to talk through, so I'm just gonna jump right in. So the term climate change, you've heard various terms that all pretty much mean the same thing: global warming, the greenhouse effect, climate change, climate variability and uncertainty. That latter term is the term we were directed to use in Texas when the politicians didn't want us at state agencies to use that term climate change. But essentially, they all mean the impact that greenhouse gases have on our Earth. And those greenhouse gases, carbon dioxide, methane, nitrous oxide, other gases, act like a blanket to trap heat in the Earth's atmosphere and result in an increase in global temperatures. And it's the same effect that you notice when you get into your car at this time of year, where it's, might be 120 inside when it's only 85 outside. And the same effect, of course, where the name has come from on greenhouses, allows you to grow plants when the temperatures are below freezing outside. So that's what we're talking about here. And the idea of the greenhouse effect is not a new one. The ancient Greeks talked about or speculated that cutting down trees might impact local weather, at least. But in the, quite a long time ago, in the 1930s, scientists and meteorologists started noticing temperatures going up gradually. And in the 1950s, scientists who were monitoring CO2 levels started noticing some pretty interesting increases, and them and others postulated this potential greenhouse effect. There are other gases, obviously, than carbon dioxide, for example, methane and nitrous oxide, and water as well. When people talk about the greenhouse effect, some people dismiss it because they talk about previous ice ages. We've had ice ages before, so maybe it'll be a little bit warmer in the future, but it was a lot colder in the past and has been warmer in the past as well. Those things that happened in the past happened really on a geological scale, not on the time frame that we're seeing right now. We're seeing some really rapid changes. Sunspots and the solar radiation, of course, is the main driver to the energy balance on Earth. And the amount of radiation, the amount of solar radiation we get on Earth does change a little bit. In fact, the sun seems to be on some sort of a heartbeat or a cyclical thing. And in fact, some scientists are expecting that we're going to get a fairly significant reduction in solar radiation sometime in the 2030 to 2050 time frame that might help mitigate what we're seeing as a result of the greenhouse effect. But sun activity, of course, does influence temperatures. The previous ice age that we saw lasted for a long, long time, something like 2.5 million years ago to about 11,000 or so years ago, and covered a good part of the Earth, including a good part of North America as well. And there's been 5 of those that we've seen in the past 4.6 or so billion years that the Earth has been around, including lots and lots and lots of mini ice ages. But the general consensus is that those slight variations in solar radiation that we've been seeing over the last few decades are having a much smaller impact on global temperatures than the greenhouse effect. Volcanoes, on the other hand, can have an almost immediate impact on temperatures because they reflect that solar radiation coming in. And there's been some notable eruptions in the past. Mount Tambora in Indonesia in 1815 was termed that subsequent summer was termed the year without summer, because so much of that solar radiation was reflected back, and the temperatures did drop significantly as a result of that. And actually a lot of people died as a result of that. Same for the eruption of Mount Krakatoa in 1883, where something like 36,000 people died for that. Maybe a more famous eruption is Mount Vesuvius, and we still to this day are unearthing artifacts and bodies in Pompeii as a result of that eruption in AD 79. But dust in the atmosphere, and dust can get there from various sources, of course, including cars that are emitting, when you see a car going down a road emitting a lot of black smoke, that's dust that ends up in the atmosphere and can reflect that solar radiation and reduce temperatures if it's there in enough of a quantity. And that's true as well for power stations. So power stations and factories, when they're putting what we see as pollution into the atmosphere, typically, certainly with a power station, there's a lot of carbon dioxide and maybe some other greenhouse gases going into the atmosphere, but it's also putting out a lot of dust that somewhat mitigates that impact. And I think many people would argue that the local air pollution caused by those power plants is a much greater concern than the greenhouse gases those things are emitting. And the World Health Organization estimates that about 4.5 million people die a year as a result of air pollution, not just from power plants, but air pollution in general, factories and cars and whatnot. And that, even in a place with good regulations and a fairly small density of population like the US, it's still something like 100,000 people that die in the US as a result of air pollution. But like I said, those dust particles do have an effect of reflecting that solar radiation back in. So it's not just the carbon dioxide that is put out by these places that affects our climate, but also the dust particles. You've heard people talk about ultraviolet radiation and the ozone layer, and that's a completely, slightly related, but completely different thing than the greenhouse effect that we're talking about. So what are we seeing on the ground? So historical temperatures, by the way, thermometers or at least mercury thermometers were invented back in the 1700s. So any temperature record that you see before that has been reconstructed from various different sources, and we could do a whole other lecture on that topic. But what we have seen since about the 1930s is a pretty strong trend in increasing global temperatures. And in fact, according to NOAA, the 20 warmest years on record have been in the last 22 years. So there's a pretty significant signal that we're seeing. And this temperature record has been put together based on satellite observations and on the ground thermometers around the place. And so, you know, when people think about that global temperature increase, they're prone to say, well, you know, what does that mean to me? And what we're seeing as well is a sort of a gradual increase in those global temperatures is an increase in the number of record high temperatures and a decrease in the number of record low temperatures. Those record lows are still occurring, but they're occurring at a much lower frequency than they had in the past. So that's a trend that we're also seeing. We're also, you know, if you're one of those people that has to see it to believe it, you know, we're also seeing things on the ground, so to speak. So we see glaciers retreating, and the image there on the left shows the Peterson Glacier in Wyoming retreating over the last, you know, almost 100 years. And satellite imagery shows retreating of glaciers all around the world. I think that one there is in Greenland. And you can see a pretty distinct trend of retreat of that glacier over the years. So that's something that is very observable. And the more warming is occurring at the poles than is occurring at the equator. And you can see that also from the temperature sensors and satellite data from those places. And that rate of decline is more or less linear at the moment in the North Pole, but corresponds to quite a dramatic decrease in the ice coverage of the North Pole. At least it's reducing by about 15,000 square miles per year, which is pretty significant. Amongst the community that are climate change skeptics or just wanting to stir the pot, so to speak, people say, well, you know, hey, the glacier in my backyard or a glacier that I visited last year was actually growing, so climate change is a hoax. And it's true that some glaciers are growing because they're getting more, typically because they're getting more snow than they had in the past, which is a direct result of global warming in their particular part of the world. But the vast majority of those glaciers around the world are shrinking. By the way, there's this guy, I'm not going to give you his name, but there's a guy who's put an incredible amount of material out there, mostly false, about the glaciers in Glacier National Park. And he's putting information out there under a fictitious university name, claiming that the glaciers in Glacier National Park are growing, and there's a big conspiracy about them actually shrinking. So that's kind of interesting. There's a lot of misinformation out there in the climate science community. Another thing that we're noticing as well is an increase in ocean levels, seawater levels around the world. And that's a result of two different things. Obviously, when the ice in the polar regions, at least the polar regions that are sitting on land, when that ice is melting, that water has to go somewhere and is typically ending up in the ocean. That's particularly important in the Antarctic, where all of that ice mass is sitting on land, but also in Greenland. And you heard probably in the news about the incredible rate of loss of ice in Greenland right now. And that's obviously contributing to increases in sea level. The other thing that's going on with sea level, at least the other thing that's causing sea level to rise, is increase in temperature. And when the temperature of water increases, it expands a little bit. And so as those oceans are warming up, they're expanding, causing sea level rise as well. And the proportion there at the moment is about 25-75, with 75% of that sea level rise being as a result of ice melt, with the rest being increase in that thermal mass. So this has implications all around the world, of course. There's places like Bangladesh, which are very, very low-lying areas and suffer from monsoons and storm surges and floods all the time. And places like Holland, where they're a little bit more sophisticated in holding that sea back, but have now decided that it's going to be a hopeless effort in the long term, and are beginning to abandon some of those areas that are low-lying or even below sea level. But it's a problem in the US as well. And, you know, there's a lot of population. In fact, the demographics in the US are such that people are moving to coastal areas more so than inland areas. And often, I mean, who doesn't want a beachfront property? But, you know, those areas are truly threatened by sea level rise. And it's not the sort of 1/4 inch per year sea level rise that we're seeing currently that's a threat necessarily, but it's the accumulation or the trend in the future, as well as what happens during, you know, a large hurricane. So those storm surges are larger than they were in the past, and the sea level rise is compounding that effect. But the statistics shown in this figure, it's hard to imagine really, but 5 million people in the US are living at elevation below 4 feet above mean sea level right now. And perhaps just as alarmingly, there's 287 energy facilities, some of them nuclear plants, other coal-fired generation plants that are right on the coast. And they're on the coast because they are using seawater in the cooling process. But nevertheless, they are also vulnerable. By the way, there's an interesting statistic the USGS put out that said if all glaciers in the world melted, which is not going to happen in our lifetime, I guarantee it. But if all of those glaciers melted around the world, the sea would be 230 feet higher than it is right now. So let's talk briefly about hurricanes. And you know, you were all saw and were alarmed probably by the Hurricane Harvey. And subsequent heavy rainfall that occurred just a few months later. But, you know, in the last 3 years, we've had 3 500-year flood events in the Houston area. And anyone who is a gambler or who dabbles in statistics knows that that's extremely unlikely to occur. So what's going on in there? The link between extreme precipitation events and hurricanes to climate change is much more tenuous. It's really not quite as obviously a connection there. But the truth is that hurricanes now are bigger, they're longer lasting, and have more rain than in the past. That's a trend that we've seen. And in fact, in the past 2 to 3 years, hurricanes Harvey, Irma, Maria, Florence, Michael, and Dorian have all broken records. And we've been tracking hurricanes and measuring hurricanes for a long, long time. So that's a pretty impressive statistic right there. And the same thing is happening in other parts of the world where those hurricanes are called different things, but essentially is the same process going on. And really, it's to do with sea temperature. And you've probably seen this in the news. Higher sea temperatures result in higher or bigger hurricanes. And what's going on there is when those sea surface temperatures are higher, actually, let me back up a little bit. When global temperatures are higher and those ocean temperatures are higher, not only does that sea surface result in a large sea surface temperature result in a large hurricane, but it is not reduced by the subsequent stirring up of colder water in the past. That colder water that gets stirred up down to 400 or 500 feet is warmer than it was in the past. So there's less mitigation of that hurricane than there was previously. And there's an interesting paper by Trenberth in 2018 that states emphatically that these events, the ones I've described above, would not have happened the way they did without human-induced climate change and warmer oceans. So he's pretty confident that there's a strong link between the two. And in fact, in Texas, we're in the process of revising our precipitation frequency maps, and we use this for building infrastructure. When you're building a house near a river or you're building a bridge, you need to know what to expect in terms of flood magnitude and precipitation totals with some degree of certainty for a particular frequency. So, for example, FEMA states that you're not allowed to build, this is administered at the state level, but you're not allowed to build within the 100-year floodplain of a river. But when you change the frequency of precipitation, and in the Austin area, for example, that's gone up from 10 to 13 inches just in the last 2 years for a 100-year event, that significantly changes the floodplain. So those houses that were previously outside of the floodplain may now be inside of the floodplain as a result of these revised precipitation frequency maps. And this is a process that Texas is going through right now, revising those floodplain maps as are other areas. So regardless of whether you believe that humans have caused climate change, there's definitely amongst scientists and engineers and policymakers in Texas the understanding that the 100-year event may be bigger now and in the future than it was in the past, based on what we're seeing in the statistics. So I talked previously about carbon dioxide levels going up, and they've gone up significantly more recently. This is the plot on the top left shows carbon dioxide levels, how they've changed historically in the past 800,000 years. And what we're seeing now are carbon dioxide levels much higher than we've ever seen before. And we're also seeing this trend in temperature, but that doesn't necessarily mean the two are related. And this graph below always makes me chuckle. It shows the correlation between the number of people who drowned in a falling pool, or by falling into a pool, and the number of films Nicolas Cage appeared in on an annual basis, on a year-by-year basis. And it looks like there's a pretty strong correlation. There's probably not, at least I hope there's not a strong relationship, actual relationship between the two. That's just a coincidence. But scientists, being scientists, want to prove for themselves that there really is a relationship between carbon dioxide levels and temperatures. And if you look back historically, and again, these temperature records as well as the carbon dioxide records have been pieced together based on other evidence such as tree rings and stalagmites and oxygen levels in bugs found in glacial lakes and all kinds of different sources, but shows a pretty compelling link between carbon dioxide levels and temperature going back a long, long time. That still doesn't mean that there's necessarily the two are related. And so climate scientists like to build models. And these global models are based basically on the energy balance. So we know how much incoming solar radiation is, and we know how much solar radiation is reflected. And when the Earth is in balance, those two are in balance. So we have as much solar radiation or energy radiation, energy leaving the Earth as energy is coming into the Earth. And the processes are quite complicated, of course, with incoming solar radiation being reflected by clouds and greenhouse gases holding that solar radiation in. By the way, if we didn't have any greenhouse gases at all, the world would be inhabitable. There wouldn't be any plant life or anything. It would be much too cold to live on. So it's just as well we do have greenhouse gases out there. The problem is that the quantity of greenhouse gases is increasing, and that's upsetting the energy balance here. But those climate models are seeking to model all of the things that you see in this figure on a grid by grid basis for the entire globe. And so by definition or by need, they're having to make a lot of approximations. And of course, we've got the butterfly effect, which you've all heard of, which means that you can't predict what's going to happen. You can't predict the weather more than a few hours ahead, probably, and not very reliably beyond 5 years. If you're the least bit interested in weather forecasting and climate models, you should do a Google search on the butterfly effect and chaos theory. It's pretty interesting stuff. But there's a difference between what scientists and engineers are trying to do with weather models versus what they're trying to do with climate models. The physics is the same, but there's a reason that weather models, weather predictions really fall off pretty rapidly after a few days, and really not much use at all after about 5 days. And people who are the climate change deniers or skeptics often say, well, you know, if the weather models can't do better than 5 days ahead, how do you expect to be able to see 100 years ahead with a climate model? And those two models are different things. They're doing different things. It's the same physics, like I said, but the climate models are not trying to predict what the temperature is going to be at, or even what the weather is going to be like on, you know, January 1st, 2100. What they're trying to do is give scientists an idea of what to expect with weather in the future, many, many years ahead. And they run those models many times with different boundary conditions, different perturbations, to get an idea of whether there'll be more rainfall in the future or less, whether the droughts will be worse in the future or less, what precipitation will be like, and what temperature will be like in the future. But like I said, it's very, very complicated. And even the most powerful computers in the world are not going to be able to get it right beyond a few days ahead, exactly right, the weather at least. But I think they're probably becoming increasingly good at predicting climate in decades ahead. I didn't touch on this in my previous lectures, but I wanted to talk a little bit about feedback loops. This is a term you may have seen before, but it describes what happens as a result of climate change that may exacerbate or mitigate the effects of climate change. And one of those is ocean warming. So as the oceans are warmed up due to climate change, they are an important source or an important sink of carbon dioxide. But the problem is, as the temperature of that water warms up, their ability to hold carbon dioxide is reduced. And so if we warm up those oceans, as we warm up those oceans more and more, their ability to absorb carbon dioxide, those greenhouse gases, reduces. And in fact, they may start releasing carbon dioxide as a result. So that's an example of a positive feedback. Cloud cover is an important one, and if we're lucky, my dad will weigh in on this particular topic at the end of the session. But this is something that's modeled particularly poorly in the climate models. As temperatures increase, we're expecting, and it's normal to expect more evaporation and more clouds. And so those clouds actually reduce incoming solar radiation and to some extent mitigate the impact of global warming. And there's a fair amount of debate in amongst scientists about what that impact is and how much increased cloud cover will actually reduce that solar radiation and mitigate or reduce the impacts of climate change. So that's an interesting area of discussion. And the clouds, like I said, are very poorly modeled in those global climate models, not because the scientists don't want to put them in there, but because they're very difficult to predict where and when they will be and how big they'll be, and when water vapor turns into droplets, which is what you see in clouds. So that's a negative feedback with clouds, obviously. Another positive feedback you may have heard about in the news is melting of the permafrost, the tundra areas in those polar regions. So as that snow melts off the ground surface, instead of a white reflective surface, you get a much darker color that absorbs that incoming solar radiation much more and results in an increased amount of heat in that particular area. There's a compounding effect as well with those soils and that tundra, and that it holds a lot of carbon dioxide, which was in sort of a frozen state previously. And when it melts, it may be releasing a huge amount of methane and carbon dioxide, which will exacerbate the problem even further. There's another term that you see a lot, certainly in the scientific literature about climate change, and that's those tipping points. And a tipping point, a good analogy for people in Oklahoma and Texas, is the horse has left the barn. So at what point where is the point of no return on climate change, I guess, is an analogy there. And there are a few of them out there. One of the ones I wanted to highlight, though, was the Gulf Stream, the warm waters that move up the Atlantic Ocean and keep places like the UK and Iceland and Western Europe, and actually the Eastern Shore, Maine areas, warmer than they would be otherwise. I grew up in Montreal, and we were buried in 6 or 8 feet of snow every winter, but I was amazed to hear that or to see that we're approximately the same latitude as Paris, which gets very, very little snow every year, and that's primarily because of that Gulf Stream. And people who are the climatologists, the climate scientists, speculate that at a certain point under climate change, particularly as a result of those water melting out of Greenland in those polar regions, there may be an upset of that Gulf Stream, and it may suddenly decide the ocean's not going to flow that way and not bring those warm waters up. And if that's the case, interestingly, that whole Western Europe area, all the way, Holland and Belgium, France, the UK, Ireland, Scotland, Iceland, even up into the Nordic countries, will be a lot colder as a result of global warming than they are right now. So that's kind of an interesting tipping point. And that's an incredibly difficult thing to model. People have tried and speculated, what temperatures might cause that to happen, but that's a tricky one. So let me talk a little bit. I've mentioned how difficult those climate models are to run and to have any significant confidence in. But ultimately, what we're seeing right now is an energy imbalance. And there's a really good paper that my father sent me from Kevin Trenberth, who was at NCAR in Boulder for most of his career and has recently returned to New Zealand. But he's written the paper in a very nice way, and if you need the reference, let me know and I'll send it to you. Describing the energy imbalance now and how we know what's going on and what the result of that is. And the point is, at the moment, we've got an imbalance there with more energy coming into the Earth than is leaving the Earth. And that's causing an accumulation of heat, so to speak. And that imbalance is about 1 watt per square meter. And to put that in perspective, I know you've all seen Christmas trees before. Those fairy lights on there are about 0.3 or 0.4 watts each. So over an area of about 10 square feet, we've got about 2 fairy lights that are on more now than we've seen in the past, which is causing this imbalance. And those fairy lights individually, you can wrap your hand around them once they've been on for a while and barely feel any heat at all. But if you have 2 fairy lights per 10 square feet over the entire globe, that translates to about 430 terawatts of extra energy that's coming in and not leaving the globe. Which is a huge amount of energy, and that's why we're getting this increase in temperature, and that's why we can be confident that it's increasing in the future. To put that in perspective again, the global electricity generation currently is about 5.7 terawatts. So we've got an imbalance of 430 terawatts for the entire globe. The amount of energy that we're putting out through electrical generation across the entire globe is only 5.7 terawatts. So it's quite a significant imbalance. By the way, about 90% of that extra heat is currently being absorbed by the ocean, and that's why we're seeing those temperature increases right now. So a big uncertainty in the future, and this is not because of the models, it's not a result of the poorly simulated physics in the model, is because we don't know how much greenhouse gases, what that concentration of greenhouse gas will be in our atmosphere in the future. And if we're really aggressive with renewable energy, and reduce our carbon footprint significantly in the future, if we really take this seriously, then we could see by the end of the century a fairly minimal impact from climate change. On the other hand, if it's business as usual, then we're going to see a pretty severe impact from climate change. And depending on which model you're looking at and which scenario you're using, you're going to see widely, dramatically different forecasted temperatures in the future. And so when you're doing, and then this is something that I've been involved with most of my career, when you're doing studies of the impacts of climate change, it's really, really important to have a thoughtful discussion about what's the right emission scenario to use, what's the right model to use, in fact, and depending on what you choose or what decision you make, you're going to see pretty dramatically different results. Now, the temperatures, we have a pretty good confidence in what those temperatures will be in the future, depending on those each of those emission scenarios. Those climate models are all pretty much in agreement or close to agreement once you've chosen an emission scenario. But if you look at precipitation, on the other hand, those models are all over the place. And some models are showing much, much drier conditions in the future as a result of climate change. And other models are showing it to be much, much wetter. Again, depending on which model you use, not depending on which emission scenario you're using. So this is where it's important to be very judicious in the choice of the model, and probably to select a model that has performed historically in your part of the world much better than others. I wanted to touch briefly on impacts of climate change, and particularly on temperature increases. I know I talked a little bit about this in one of my previous classes, but temperature increases have an interesting impact on some areas of agriculture, and cotton is one I learned about not too long ago, and this impacted some farmers that I was talking with in Oklahoma. And when those nighttime temperatures don't come down quite so far, that has a very negative impact on cotton crops. And we're seeing already in Texas and Oklahoma the impact of those nighttime temperatures not coming down as much as they did in the past. And by the way, on impacts of climate change, we're typically seeing more changes in nighttime temperatures. In other words, less or warmer nighttime temperatures than we're seeing increases in the daytime temperatures. But there are some positive impacts as well, right? So the length of the growing season, for example, has increased pretty dramatically. Farmers are able to plant earlier in the season and plant and have their plants in place later in the season without the risk of frost. And for me, I mentioned I grew up in Canada, and you know, there's crops that we can grow in Canada that we weren't able to grow in the past because of the lengthening of that growing season and the risk of frost being reduced during that growing season. And the plant hardiness zones are changed. This is information, by the way, put out by the US Department of Agriculture. So there's a shifting upwards in the hardiness zone as a result of those warming temperatures. There's also, you know, shown somewhat dramatically by World Wildlife Fund and other organizations, risk to animal species. And you know, this is probably a little bit of scaremongering amongst organizations that are wanting to collect membership fees, but there's probably a serious risk to many, many, many species out there, particularly amphibians, as a result of climate change and their inability to adapt to those rapid changes. Coral reefs, I talked about in one of my previous lectures as well. There's a double-edged sword here with coral reefs, in that they're very, very sensitive to temperatures. And bleaching events is what we're talking about right there with increased temperatures. But also, as those oceans absorb more carbon dioxide, the acidity levels change as well. And the corals are also very, very sensitive to acidity levels. So they're kind of being attacked by both sides. And we're seeing some pretty dramatic impacts in the Great Barrier Reef and other areas with coral reefs. Closer to home, this is west of where I live in Dripping Springs. There's a large industry in growing peaches, and when we don't have those winter temperatures that are low enough, in other words, days below freezing, then there's a pretty bad impact to the peach trees. And interestingly, this may be a totally economic thing, but I drove through Fredericksburg 2 weeks ago, and many of the peach orchards have been cut down and instead vineyards put up. And like I said, it may be that Texans have more of a taste for wine now than in the past, rather than peach cobbler. But I thought that was an interesting thing and wondered whether that's because of a series of failed peach crops over the last few years. On the hydrology side of things, which is my passion, there's in areas where there's snow melt dominated, in other words, big rivers that originate, their headwaters are in the snowy mountains. We're expecting a shift in the hydrology. So we're expecting runoff to occur earlier in the year, and the total runoff, volume of runoff to be less than the past. And in California and Oregon, places like that, we're seeing this impact already pretty significantly. But in general, and I can make this generalization for the entire world, we're expecting the wet places to get wetter and the dry places to get drier. So that's kind of a bummer, for lack of a better word. You know, in places that are really wet already, we don't need any more water, and the places that are dry, we need that water, and yet they're going to be drier in the future. So as a water planner, that's a pretty good rule of thumb to use when working with water suppliers and water users in these particular basins. And like I said, this is something that I've discovered discovered in the literature, but also seen in the model results that I've been working with on my hydrological models. I would be remiss if I didn't mention some of the skepticism out there on climate change. You know, scientists by definition are rarely agree with one another, and that's a good thing. It's good to be skeptical about information that you see, and certainly I don't expect you to believe everything I've told you in this lecture. I hope that you go and do your own research. But there's some notable skeptics out there that I just wanted to point out what they were thinking. John Christie at University of Alabama has produced some really good articles on temperature increases, and we rely very heavily on satellite data now to track temperature increases in the future, or that were observed. And he said, and he's worked with this data, in fact, he helped set up the algorithms to calculate temperature. He thinks that the temperature data being reported is exaggerated a little bit, not properly processed. So there's probably some merit in that. Judith Curry, who was at Georgia Tech, and she's now retired, but she has stated pretty emphatically and presented some pretty compelling arguments that the uncertainty of those models is higher than we're stating. So there's probably some truth to what she said as well. Richard Lindzen at MIT and my dad, who's on this webinar, at least he was before, have a bee in their bonnet about clouds and how poorly they're modeled by the climate models, and how clouds hopefully will mitigate the impacts of climate change more than a lot of people are saying. And I think a lot of scientists out there as well are somewhat skeptical or somewhat irritated by the amount of money that's spent on developing climate change models and buying supercomputers and all of that, when we've really got some pressing environmental concerns that we could deal with right now, like air pollution, like water pollution, you know, plastics in our environment, things like that. So there's a lot of people that feel that way. I think, though, the bottom line, and I think everyone would agree with this, frankly, including the people listed here, is that our climate is changing, and it's largely because of human activities. Now, we can talk about what those impacts are and what the future holds for us. I think there'll be some healthy discourse on that, but I think overall people are in agreement, at least scientists are in agreement, that climate is changing, and it's because of what we're doing, and that's what it is. I think in the US, turning to the US, this is not so much the case in other countries, but in the US, the history has been you know, climate change is not happening, it's a hoax. But that's progressed into, you know, it's happening, but it's not really our fault, or it's not as bad as some people think, or there's more pressing issues. And I think most people have moved now towards acceptance that it's happening, that it's our fault. In other words, it's as a result of the greenhouse effect, but that it's too expensive to fix. You know, it hampers economic growth, or, you know, it's too expensive to move people out of those coastal areas, or those environmental issues are more pressing. Or also I've heard the argument that economics will take care of it. As people have their houses flooded, they're going to move away from the coast anyway. And I think really where we need to be is a healthy discourse on mitigation and adaptation. In other words, how much money and effort do we spend addressing these issues? And there's a balance there, of course. We can't just drop everything and focus strictly on mitigation and adaptation of climate change. But I do think that we need to have a conversation about it. The other interesting thing is, unlike pollution, which typically is a local issue, climate change really needs to be tackled on a global basis. And countries get together on a regular, or at least in the past, have got together on a regular basis to discuss what they can do to deal with climate change and reduce greenhouse gases. And there was a Paris Agreement in place. I guess it's still in place, but some countries have backed out of that right now. But that type of agreement sets some guidelines for the local level, for local implementation, where we would be able to, as a country or as a globe, as an Earth citizen, be able to start reducing greenhouse gases and do something about that. I think where we need to be, though, is in adaptation and mitigation, and that's something that we can all do. And mitigation, you know, mitigate, what does that mean really? It means how do we turn this around? How do we stop, how do we reduce greenhouse gas emission? And we do that by, you know, installing solar panels or building windmills instead of using energy from coal-fired power plants, and burning gasoline in our cars, and, you know, use public transport when it's out there, telecommuting like I'm doing today, you know, fuel standards, public education, things like that. Those are kinds of things that we can do for mitigation. And then adaptation is, you know, complementary to mitigation, but it's like, all right, this is going to happen. How do we deal with it? And that's, you know, moving away from the coast, moving out of the floodplain, planting different types of crops, or planting those crops in different places, and then putting up infrastructure, whether it's flood barriers or other things to deal with it. So I think where we need to be right now is on mitigation and adaptation. And I think the question, though, is how much effort we spend on that. And that's something that a discourse that needs to occur in the public, amongst policymakers. But I think I've used up my time, Christine. So this last slide, actually, this picture was taken in Iceland last summer. I went there on vacation with my family. That's my 8-year-old son, Miles, and we're standing at the foot of a glacier over there. Iceland's a fascinating place to visit. It's actually fairly easy to get to. There are direct flights from Dallas. But those glaciers in Iceland are retreating at about 15 square miles per year, so don't wait too long before you go.
Thank you so much. We have some time for questions, so who would like to break the ice and ask the first question?
I'll go.
Thank you, Catherine.
I actually want to hear what your dad has to say about clouds.
Awesome. You put him on the spot, which is great.
Oh, and can we have that paper as well? Sorry for interrupting.
Yeah, I will send that to Dr. Pappas after this class, and she can circulate it to the folks here.
Right. Thank you.
Sure.
So we're gonna ask. Do I need to ask him?
Jeff, you're on the spot. Did you hear the question?
He's got to unmute.
You need to unmute yourself. We can't hear you, Jeff. His audio might not be working.
You may have to call him. Oh, darn.
There we go. We do a family Zoom call every week, so he should have figured out this process by now. Oh no, still not. We can't hear you, Jeff.
He's talking.
Yeah.
Oh.
That's too bad. Let me see if, can I unmute? You're muted, Jeff. So I think it's not your microphone that's not working. You're on mute. All right, sorry about that.
I messaged him.
Okay. Anyone else? Questions? I went through a lot of material. Some of it was in my previous lectures.
We have a question from Laura. Do you think we could, oh shoot, it went away.